Hi, and welcome again to my Physics Online video lecture series. Today's video, we're going to be talking about vectors in more than one dimension. And again, the focus here is going to predominantly be on vectors in a kinematic sense, since that's what you should have covered at this point in the semester. But I wanted to talk about what do vectors look like, or what do these vector quantities look like, more accurately, when we are working in more than one dimension. So we can begin with a little bit of a review of sorts by essentially recalling what we've done previously for vectors. So one thing is that there are some quantities which are vector quantities. So some quantities in physics, such as position, displacement, velocity, acceleration, these are vector quantities. Others are scalar quantities. Distance traveled, speed of the object. To some extent, you could say direction is quasi-scalar. It's a plus or minus sign, but really adding a direction to stuff is what makes a scalar into a vector. Other examples of scalar quantities that we've encountered so far, or may have encountered so far, would be things like density or mass or volume, that kind of thing. Although there are other quantities that you might expect to be a scalar which are in fact vectors. For example, area is actually a vector in physics, but we don't have to worry too much about that at this time. What else do we know about vectors? Well, they can be represented with the arrow. So represented with the arrow above the term. So for example, if you wanted a position, you would put x with a little arrow above it, like so. The other important thing is that they have magnitude and direction. Scalars have magnitude only. So magnitude and direction. And in 1D, we have represented direction using plus and minus signs. That basically means, for example, with velocity, an object which is moving to the right has a positive velocity. An object which is moving to the left typically has a negative velocity. An object that is moving upward, we might say, has a positive velocity. An object which is moving downward has a negative velocity. An object which is thrown near the Earth's surface, taking the upward direction as positive, would therefore have a negative acceleration, and so on. Okay, that's one dimension. So our kind of question and what we're doing in today's video is extending some of this. What if we allow for two or more dimensions? So what does that do to these things? Well, direction and magnitude are still valid in two dimensions. We can still represent the vector with an arrow above it. Where we run into trouble is this thing about plus and minus. Plus and minus. The reason why we might run into trouble with this is if we're just simply trying to represent a velocity, let's say. And rather than heading in a direction that is to the plus direction or the minus direction, Maybe like this right here represents the x direction and this represents the y direction. And so an object moving in the direction of either of these arrows would be considered positive in a one-dimensional motion. What if our object actually has a velocity like this? You see what the problem here is. This velocity points in the plus direction if we're looking at, is it moving left or right? It points in the minus direction if we're looking at, is it moving up or down? So do we call this a positive velocity or a negative velocity? The other question, of course, is what do we say about the magnitude? And that might be getting ahead of ourselves a little bit. So there are different ways of representing vectors, and I think a whole separate video could be made if we're doing short videos just discussing different ways of representing vectors. In fact, I plan eventually to make such a video, and it will kind of fall into this unit of study for those of you who are trying to use these videos to study a physics course. But what would we do as far as representing these using an up, down, left, right, forward, backwards kind of notation? Well, one way to represent it would be to have our position. Let's say that we are going to represent position with an R instead of an X. Oops, for some reason this thing tried to tilt my arrow. We might represent this using an X, a Y, and a Z. This right here, this is what we would call Cartesian coordinate. So this is Cartesian coordinate, and it really is Cartesian coordinate representation. So what do these coordinates tell us? Well, typically this one right here is your left and right coordinate. This becomes your forward and reverse, and Z becomes your up and down. And note that each one of these coordinates can be plus or minus. So minus if it's left, plus if it's right. Plus if it's forward, minus if it's reverse. Plus if it's up, minus if it's down. So for example, let's say that we have a displacement of 6 meters to the right, 2 meters in reverse, and 3 meters upward, and we want to express that in Cartesian coordinate representation. So my displacement, maybe we would represent this as delta R or something like that, could be written with this representation. So this is 6 meters to the right. This to the right says that it's in the x and specifically the plus x direction. So we would start with plus 6 meters, comma. Then we have 2 meters in reverse. The in reverse part, this would mean that it's negative for the y direction, so we'd have minus 2 meters, comma, and then 3 meters upward. So 3 meters upward basically means this keyword upward is the up-down part, and it specifically goes with up, which is plus z. So we'd have comma plus 3 meters. Now you can also express this, since all three have the same unit, as 6 comma negative 2 comma 3, and pull the meters out. You can also include the pluses on the 6 and the 3. They're kind of taken to be implied if as plus if you don't explicitly put a plus there. But these are different ways that you can write this validly in Cartesian representation. Okay, so coming back here to this Cartesian coordinate representation, basically you're assigning up to 3 dimensions to the object. Now sometimes, and frankly in algebra-based physics, I should say often, we end up working in 2 dimensions rather than 3. For example, most of the time when we're considering the motion of an object, that motion is considered in 2 dimensions or 1 dimension. So it may have a trajectory which is described by a parabolic arc, let's say. That's a projectile motion. Well, we only need 2 directions, a sort of forward, reverse, and up, down, or maybe a left, right, and up, down to describe this. So, you know, this is Cartesian coordinate representation in 3D. There's also a 2D equivalent, which basically has us setting one of our terms to 0. So, for example, maybe we have 0, y, comma, z. And oftentimes we simply abbreviate this to y, comma, z. Or more often we really abbreviate this by removing the z term rather than the x term. Okay, so this is very common. We might say or r is represented by x, comma, y, comma, 0, which is just simply x, comma, y. You know, either of those is correct. This one right here fits more naturally with what's going on in 3D if what you're looking at is a projectile motion. The object is fired forward and maybe above the horizontal, and so it, you know, does one of these things, like so. And so this direction right here is the forward reverse direction, or maybe it's the left right direction. And this direction here would be the up down. So this is up, this is forward. But very commonly we just revert to calling this x and y rather than y and z. So hopefully that particular point doesn't end up being confusing to those of you who are watching. I'm not especially pedantic about how you label things here when I'm teaching my courses. I care more about, do you understand that the thing has a component of motion that's forward, reverse, or left, right, and another separate component that is up and down. Okay, but that is sort of like a primer, I guess you could say, on vectors in more than 1 dimension. We will, like I said in a future video, have occasion to look at other coordinate bases, and eventually also how to convert from one coordinate basis to the other. But for now, I think that's enough for today. So thanks for watching, and hopefully you have a better understanding of this idea.